Okay, so what I will be explaining today is a question from the past paper of an OCR past paper, July 2017, and it starts with this example. A swimming pool designer investigates the depth D below a water surface reached by a diver when diving from a height h above the water surface. The designer models the diver as a uniform wooden cylinder. The experimental arrangement is as shown in figure 18.1. What we have here is a wooden cylinder, a trapdoor, and eventually the door opens and the wooden cylinder falls inside the pool. The first sub question asks for the density of the wood, and it gives us some information. The wooden cylinder has a mass of 5 × 10⁻³ kilograms, diameter 1.0 × 10⁻² meters, and the length 7 × 10⁻² meters. And it needs us to calculate the density. So if I write AI, we know that the formula for the density is mass over volume. We are given the mass, so the only unknown would be the volume, right? Oops, I shouldn't have wrote equal here. So if we go to find the volume of the cylinder, we know that the formula for the volume of the cylinder is pi times d squared divided by 4 times the length of the cylinder, right? Is equal to pi times 0.01 squared divided by 4 times 0.07, and volume equals, if I use my calculator, we're gonna find out pi times 0.01 squared times divided by 4 times 0.07 is equal to 5.5 times 10⁻⁶. 5.5 times 10⁻⁶ meters cubed. Now that we know the volume, we can find the density, and that would be 5.0 times 10⁻³ divided by 5.5 times 10⁻⁶. We'll know that we can do some simplification here, and what we get is 5 divided by 5.5 times 10⁻³, and that is equal to 910 kilograms per meter cubed, and that's on 3 significant figures. Okay, let's move to II. Suggest why wood is an appropriate material to model the depth reached by a diver. So what you need to think here is that you have to find a way to compare wood with a diver, so eventually a human body. So one of the answers that will give you one of the 2 points here is that the wood has a fairly similar density to a human body. That will give you the first answer, and then you need to think of, okay, the divers float in the water, so as the wood. So if the wood floats in the water, that means that the wood's density is less than the density of the water, right? So the wood's density is less than the density of the water, and that should give you the 2 points. Right, let's move on to the next page. B. Okay, the cylinder is released from rest from a trapdoor. The base of the cylinder is at height h equals 0.3 meters above the water surface. Calculate the speed of the cylinder just before the base hits the water and ignore air resistance. What I've included here is that we need to use Suvat equations in order to find that. So if I go on and write Suvat here and identify what we are given from the exercise is good to write all the known stuff down here, so it will be easier for you to choose the appropriate formula to use. S is equal to h, and we're given it as 0.30 meters, right? It says that the cylinder is released from rest, so we know that u, the initial velocity, is 0. V is what we are asked to find. The final velocity is the speed of the cylinder just before the base hits the water, so I'm gonna put a question mark on that one. And A is the gravitational acceleration in meters per second squared. And time, we don't need that for that example. We don't need time for this example. So if we go on and see what we have from the exercise, we can see that the right formula to use is this one. We're looking for the final, we know the initial, we know gravitational acceleration, and we know the distance, right? So we go on and find the final velocity. If I cancel u, because it's 0, as mentioned earlier, what we get is square root 2 times the gravitational acceleration times 0.3, which is the height of the falling object. And v is equal to, if I use my calculator again, that would be 2 times 9.81 times 0.3, 2.43 in 3 significant figures, remember. 2.43 meters per second. C. Figure 18.2 shows the cylinder fully submerged under the water surface before it has come to rest. The cylinder is moving vertically down. I. Add arrows to figure 18.2 to show the 3 forces acting on the wooden cylinder and label the arrows. Okay, so free body diagram of the wooden cylinder, and what we're gonna have here is the weight pointing downwards, of course. So one will be the weight of the cylinder. Right, we do. Okay, and in an upward direction, we're gonna have 2 forces. One is the force acting from the water to an object, and is known as the buoyancy force, or we can write it down as upthrust. And the second one would be the drag force. Oops, excuse me, drag force. 3 forces. Describe and explain how the resultant force on the wooden cylinder varies from the moment the cylinder is fully submerged until it reaches the deepest point. And it gives 3 points for that. It's important for you to notice how many points it gives. Sometimes it's a clue to tell you how many answers you should provide. That would save you some time. Sometimes. So, if I just write I here, and I'm gonna write I, that we solved it right here. I, gonna mention it in text. Okay. First thing that we need to notice, realize, I'd say, is that the resultant force of the object, obviously we have an object moving downwards towards the water, and it's going deeper and deeper until it stops and it starts floating towards the surface, right? It starts moving towards the surface, upwards. So the resultant force decreases with time as the cylinder descends, right? The resultant force decreases with time as the cylinder descends. Hope I wrote descends wrong. Yeah. Okay. That should give you 1 point. And second point would be just make a few statements that the weight remains constant. And the drag force is eventually going to reach a value of 0 as the object reaches its lowest point, meaning that, sorry, you can say that lowest point, meaning that when the object reaches its lowest point, the velocity at that point, the velocity of the object, would be 0. So as the drag force, because the drag force is proportional to the velocity, and the bigger the velocity, the bigger the drag force, and the opposite, of course. Okay. That should give you the second point. And the last statement we should make is about the resultant force. Obviously, as the object sinks into the water, the upthrust will increase due to pressure. We know, if I prove this with a formula, we know that the pressure is equal to rho GH, and the pressure is also equal to force over area. Rho GH, that's the density, gravitational acceleration, and the depth of the object inside the liquid, whatever, water or whatever. So we can see that the depth is proportional to the pressure, and the pressure is proportional to the force. Okay, so the last point would be, at the lowest point, the resultant force is upwards. And what we can write in brackets is that the upthrust is bigger than the weight. Okay, great. I may have time for the third page as well. Let's try